let me continue and in a short recap of what I said at the end of yesterday's class to go over it, because probably it's one of the most important points in the whole course, and that justifies why the action is a good matter candidate. Let me go back to one slide or two. So then we said that we have these two cosmological scenarios for the action: the pre-inflation and post-inflation. They didn't know whether the PJ green.
Yes, this is on your left. Just the small thing, the dash. Yes, so you can put it downstairs somewhere. No, you're sorry, I'm wrong. Sorry, my fault. Yeah, you're right. I'll move it away. Just keep going.
Okay. So depending on whether the PJ Queen transition happens before or after inflation. No? So in the pre-inflation scenario, so in the two different scenarios, we have different ways to different evolution of the action field and different ways to compute the density, expected density of actions of color matter actions from the parameters. Basically, this initial misalignment angle and the action mass. For the pre-inflation scenario, the situation is very simple in terms of computation. We have only the contribution from the realignment effect or misalignment effect. But on the other hand, we have this unknown parameter that is this initial angle. So this spoils a little bit the predictability of the model. And in principle, this can be fine-tuned to get practically the right matter density for many values of the action mass. On the other hand, in the post-inflation scenario, we don't have this freedom in the parameters because we can adopt an average value of this angle, because in fact the universe is populated with many different patches with different values for this initial misalignment. And then you can average this. It's justified because these patches are taken randomly from the whole domain of values from 0 to 2 pi. And therefore, this gives a relatively robust prediction around 30 microdecamol, but this is not enough because we have this topological effects contribution, and this is much more uncertain. And this, again, for different reasons, also spoils a little bit the predictability of which is the right action mass to get the dark matter. So at the end, this a little bit summarizes the situation. What is the best mass value for the action to get right dark matter? And at the end, basically, almost any mass value can have a model with a right dark matter density. So for pre-inflation models, one tends to have slightly lower masses. So this blue line corresponds to the action masses for pre-inflation models, and the fact that it's so big reflects this dependency with the initial misalignment angle. If you have angles of the order of unity, which could be considered natural in some sense, then you get values in the ballpark of 10 to minus 6, 10 to minus 4. But as I said before, you can get fine-tuned values of this angle and get to very low, almost arbitrarily low values of this angle. Yeah.
Thanks. So thank you.
Is the right way to be thinking about the pre-inflationary models that the regions that were in causal contact at the time of production, those are the ones in which the theta angle is going to be the same in the later universe? Like those are the regions in which theta will be the same?
in the pre-inflation models,
Mhm.
one of these regions is going to be the one relevant for our universe, our subborn universe.
And is the region that's relevant, like if you trace it back to the time of production, will that whole region have been in causal contact at that time?
At that time,
At the time of production?
I don't know if I understand the question. So at the time of all these different passes that have different values of theta are disconnected regions, are causally disconnected regions at that time. And then whether at pre-inflation or post-inflation, but the inflation will select one of them to be the whole observable universe right now.
So are the patches themselves the regions that at the time of production were in causal contact? Like is the patch defined
Yes.
by what's in causal contact? Okay, at the time of production.
At the time of
Okay, thank you.
Okay, so then we have this this window of possible values. Sometimes this one at the very low masses are called anthropic window because of the reasons I mentioned before, that you can argue for a very low value of this initial angle in order to get the right matter density at so low masses. So in principle, you can have very low action masses and have the right matter density. Remember that for a particular model, if the density of that matter is roughly inversely proportional to the mass. So for a particular model, you will have a lower bound on the mass, below which you have too much matter density. But in general, for all models collectively, you can always find a right initial angle that allows the right matter density for that action mass. For the post-inflation models, you don't have this freedom, so you have a real cutoff here. You have a lower bound on the mass, below which you have too much matter density, but above which, given the uncertainty in computation of the relic density from topological defects, you cannot be more predictive than this, and you still have a relatively large values of masses for which you can have the right matter density. And this one here is this domain wall number higher than 1. So these models are either ruled out because they are not cosmologically viable, or you need to modify them somehow to break this degeneracy. And in that case, it pushes this region to higher masses. So you could still have your matter density even to so high action masses. So okay, this is roughly the situation, and I have this plot here, which is again I will comment this back in the experiment classes tomorrow and after tomorrow. This is the same plot as before, with instead of showing here the dimensional coupling, I'm showing here the adimensional coupling, the C. So this yellow band, which is the same as before, is now horizontal instead of being like that. So that is the same type of plot: action, photon coupling, and mass, with experimental results and projections, and overimposed with these bands to show that most of the activity that is taking place experimentally traditionally is correlated with the pre-inflation line, but that now increase experimental activity both to lower masses and also especially to higher masses with respect to ADMS, which is let's say the pioneer in this type of searches. I will come back this later. Another plot that I like to show. This is from a paper from Huth and collaborators. They made a Bayesian analysis of all these arguments that they have been presenting a little bit qualitatively. Bayesian analysis, Bayesian statistics allows us to assign probabilities to theoretical statements. So it's a nice way to quantify a little bit our degree of confidence over unknown facts or like for example, whether the action exists and what is the mass of the action. Of course, this type of analysis are always somehow subjective, and this subjectiveness is encoded mathematically in the so-called Bayesian prior, and you have to explain always what you're assuming in your analysis, and for details I refer to this, but you have here the same plot as before, action photon coupling, action mass, and this is a map of our Bayesian posterior probability. So what are our information, the information the authors used in this analysis is projected in our degree of confidence where the action is, assuming the action is dark matter. This is an important information that it was included in the analysis. And you can see that, okay, well, this a little bit maps these bars that I was plotting before. This is 10 to the minus 6 and until a fraction of the electron will 10 to the minus 2 or so. And you see that in principle, much lower masses than this are not excluded as dark matter candidate, but somehow our confidence in these models slowly fades away, no? Because there are so many orders of magnitude there. And this whole here is the ADMX results, which is the only significant experimental result that are so far really excluding action models as dark matter, and that's why it starts depopulating this probability. And this here is also helioscope experiments that are robustly excluding the action photon coming from the upper side, so somehow constraining the space where the action can live. So it's a nice plot. So, to conclude the cosmology part of this course, I want to mention also that so far I have been focused on the action, usually the action as dark matter candidate, what this entails, but a more generic ALP can also be dark matter. In that case, you are free from many constraints from modeling, and you are free to build a model in practically every point in the parameter space. And okay, there is an important paper in this respect, which is the one I mentioned down here, where basically they, under very general assumptions, they show that a generic version of the misalignment field can also take place with a generic ALP. So we have practically the same or very similar story as the one I mentioned before, but with the freedom to have all dark matter in a big fraction of the parameter space. Okay, there is a very specific subset of models that are called alchemical models, in which the prediction of the models are much more enhanced. These are models in which the ALP is used also as the inflaton. So they're interested in the fact that they mix the same ingredient to explain both inflation and dark matter, and this is a very specific region in the parameter space, which turned out to be well at reach of experiments, so that's why it's a bit interesting. But from the point of view, I'm not an expert in inflation, but from the point of view of inflation, they are not particularly motivated. It's just that it's a very specific case in which it has a good prediction in terms of ALP's properties. Yes.
Thanks. I noticed on your one-dimensional mass plot that the ALP miracle only is overlapping with the section where your number of domain walls is greater than 1, which I know you said is problematic in axion models. Do ALPs run into the same problem with the topological defects?
No, not necessarily. I mean, it's probably misleading to have put this ALP miracle in that one-dimensional plot. It's just because it coincides in this mass range, but this one-dimensional line is mostly QCD action, and then the ALP thing is completely different. So whether they have topological defect or not will depend on the specifics of the model. So ALPs is such a generic word that you can fit many things inside. So it does not suffer from this in principle. And then it has nothing to do also with the action band, because the action band is for the action, not for the alps. So it just by chance, these predictions of these alchemical models are close to the action band, but it's just by chance. They are not linked with the action, the action. So
So what makes ALPS ALPS? Is it their production mechanism?
no, this is a question that people would answer differently. I'm sure theories would answer in a different way that for me, an alp is a phenomenological definition, something that couples with the photon, similar like an action. For me, is an alp. So I can represent it as a point in this plot, but I don't say more about the model that is behind this phenomenology. Some other people would dare to say that an alp is a particle that comes from a stationary standard model that has also some symmetry breaking or some symmetry, and is a bit closer related with an action. Okay. I don't think there is a fixed definition in this sense. Okay, so I think the main message here is, yeah, you have QCD actions are good matter candidates, ALPS can be good matter candidates also, but you have much more freedom in the parameters. There are a number of other implications, cosmological implications of actions and ALPS that I listed shortly in my notes. So I don't want to go too much into detail here, but ALPS are very versatile particles. They have been involved in many scenarios, not necessarily linked with our matter. Actions are candidates to be the inflaton, for example. There are many model building using actions or action-like particles as inflaton and then be part of inflation itself. They can be Holter matter. This is something I already mentioned. If the action is in the electron volt scale, they will produce thermally and produce a relativistic population of particles, and to the extent that can be in tension with observation. So this can be translated on an upper bound of the action mass of a fraction of electron volt. If actions are slightly lighter than that, then they could be dark radiation and constitute relativistic degrees of freedom at the early universe. So, and in fact, it has been computed that such a case would add an extra addition to this effective number of neutrinos, which is this parameter that parameterizes in cosmological models that radiation basically by an amount of 0.027 that is sort of a minimum. I mean, this is model dependent, as I understand, but it's a small number. It's not yet we're not yet sensitive in cosmological probes to this, but will be in the near future. So this will be very interesting to in future cosmological data to see if we need an extra relativistic degree of freedom. This would be a strong hint for some like particle in cosmology. In principle, independent from the dark matter issue. And also, there are also constraints from the CMB, from the presence or the absence of isocurvature fluctuations that are expected in some of the configurations of this cosmological models. Okay, maybe I don't enter into here, but you can take the references you're interested from the notes and explore. Yeah.
Yeah, so if VPN or another cosmological probe were able to put a constraint on that delta N effective number, what would that actually tell us about the axion particles?
Well, I think if you have a constraint, you cannot say much, only that there were no relevant population of that radiation in terms of actions at that time.
Okay.
But you could see a positive signal, and then would be really important if you have a mismatch between the expected standard model value for the effective neutrino, which is 3 point something, then this would really be a strong hint for an action-like particle or similar particle at those times.
And is that basically telling us how relativistic axions were at that time? Is that what delta N effective is telling us?
It tells that they were relativistic at that time, or there was a population of relativistic particles.
Okay, thank you.
So there are more issues, like the presence of actions would be detected at cosmological/astrophysical level. For example, we mentioned that the action decay into 2 photons. Then, okay, this decay is longer than the age of the universe, so it's not relevant regarding the stability of this particle. But it may give observable signals. Like, for example, you could look for this monochromatic decay in gammas in regions of the space where you expect an accumulation of that matter, and this has been done, and this little green thing exclusion comes from this type of observation. So the absence of this line can be translated into an exclusion in this plot, and then there are a number of other arguments also related with the presence of this action. You could expect distortions in the CND spectrum, affect the results of primordial nucleosynthesis, produce other monochromatic lines at the X-ray or gamma ray, and this gives all this set of green regions that are excluding values of it. As you can see, they are all above the value where action where action are expected, but nevertheless they are important. And you can find more information in this paper, which gathered most of these arguments. Okay, let me move now to more specific astrophysical material. Yes.
Yeah, sorry.
I'm sorry, I had a question on the previous slide for the hot dark matter. Maybe I missed this, but why is that an upper bound on the mass instead of the lower bound for thermal production of axions? So usually for light thermal dark matter, you have a lower bound in the mass, and and anything lighter is excluded. But why is it the opposite for axions?
You're talking about the hot dark matter bound.
Yeah.
This bound here.
Yeah.
So for these energies, for these masses, I think this is not specific for action. This is for any relic action at this energy, at this mass. The relic action density versus mass is increasing. So the higher the mass, you have more production of particles. And then if you go to even higher masses, then it comes back down, and then you have the dependence that are more typical for winds, which are much heavier. Then which is the higher the mass, the lower the density.
Okay.
The one we're giving for.
So can I set a lower bound on the mass of the axion by this hot dark matter? Maybe it's really light or something, or maybe run into something else.
With the hot dark matter,
Yeah.
argument,
Like the same thing that Sunny was saying, like I'm thinking that if I have light dark matter, it's gonna be hotter and hotter.
no, no, you cannot, because the lighter the mass, the smaller the amount of dark matter you get. So you could have constraint there.
Okay,
You have constraints because of the older matter, which is start to increase. So,
sure. Okay, thank you. Can you have like some model of Oxenville these could be massless? So like just like you have some kind of energy density in some region, and then this acts like a massive particle. Thinking about right, like in GR when you have like those energy matter things, or like we can describe these as a
so you're thinking about the energy, all the energy to be encoded in kinetic entities. Yeah, I guess that's possible, but then this is not older matter anymore. It will be older matter relativistic particle. Yeah, it's a possibility, but it's not so much interesting as the one we are dealing here. It fits the older matter paradigm.
But I don't know if you would say this, but you have like some lower bound from the axon method. You can go this into anything you want.
You can do, at the end of the day, you can do anything you want, because this lower bound is for a very specific model to fix your parameters. You apart from the mass, and then you lower the mass to increase the density, so you have a lower bound on the mass. But this is for a specific model. If in general, you can always play with the initial misalignment angle. If you allow it to be as small as you want, then this goes down. So this point, which is the point where you get totality of dark matter made of actions, you can move it to lower masses almost arbitrarily. So it doesn't really exist, this lower bound from these arguments.
This is my doubt, because you can lower your mass, but you can't have like a massless particle.
No,
Yeah.
well, then you run with issues like, okay, if you're in the QCD action paradigm and you lower too much the mass, this means that you're increasing the energy scale of the shaping. And then you end up putting it in the mass in the Planck scale. So does it make sense to have a shaping with an energy scale at the Planck or above the Planck scale? So this is not very appealing from the theoretical point of view. So this could be also considered a sort of a long form. Of course, you forget about QCD action and you go to Alps. You know, this facile matter that you already listened to, those are super low masses.
Okay.
It's difficult to understand as a QCD action. But it's an Alp, and I don't care about the model, then maybe you can get it. So massless it would be even lower.
And then just to follow up to that, there's no reason that our Petit-Quinn scale couldn't be above the Planck scale, right? It would just make everything weird and complicated. But like a priori, it could be that high.
You have to ask this to a theorist. I
Okay.
don't know. I don't know if it's a matter of prejudice. Like, I mean, I don't feel comfortable with such situation, or I mean, we don't know what happened with the UV completion of the standard model at those energies. So why should I? It's a bit strange. But I don't know if there is like a fundamental reason like this. This really cannot happen. This kind of work, or a theory, or it's or just a prejudice.
Okay, thanks.
maybe it's a good point to ask questions about that matter, because I'm moving now to more to astrophysics. Okay, so let me devote some time to astrophysics, because even if this is not totally related to the dark matter issue, it's important on actions, because contrary to all the dark matter candidates, actions, if they exist independently of their role in cosmology, they will have important effects in astrophysics, and this can be used to both constrain very strongly properties of actions and in some cases provide hints on their existence. So basically, I will be talking most of it in stars as action laboratories and action factories, in the sense that they not only provide a possibility to observe indirectly effects related to actions, to the presence of actions, but also they provide a source of actions that can be used for experiments. It will be a category of experiment that I will be talking tomorrow. And there is also this second effect that the propagation of photons over large distances that I will also mention. So I think that we'll be mostly talking about stellar evolution, and there is a fundamental reference in the field, that is this book by Igor, which is really very comprehensive. It's already quite old, and some of the numbers have been updated with the time, but the concepts are all there, so highly recommended as a reference for these topics. So basically, well, you know already, stellar evolution. It's basically a balance between the forces of the star due to gravity and collapsing forces due to gravity, and contrary forces due to the pressure from the nuclear fuel. And basically, this is most of it quite well known in astrophysics. These different stages in the left of the star are quite well modeled. Low mass stars go through different stages, and they end up as white dwarfs when the nuclear fuel has been exhausted, and massive stars have a different path, and that typically end up in supernova explosions, neutron stars, and in some cases black holes. So as I said, the stellar evolution is nuclear physics story. The core of the star, of a young star, is basically hydrogen, and then it starts burning hydrogen into helium, and we have a helium core being growing in the inside of the star, and later on the helium is also burned and we create heavier elements, and this basically drives the life of the star. So regarding observations, you probably know that this famous color magnitude diagram is closely linked to the life of the star. So basically, it is a bit of a cartoon version of this plot. In the y-axis, we have the magnitude, so the luminosity of the star, and on the x-axis we have spectral class, which is related to the temperature of the surface of the star. So this plot, what we see usually when observing a star is properties of the surface, but these properties are linked to the stage in the life of the star. For a particular a real observation of a population of stars placed in this plot, you have an example here. For a particular globular cluster, when one does that, usually you get a picture of where the stars are in a particular time in their life, because typically the stars in a globular cluster are expected to have the same age. So this is the so-called isochrones in this type of plot. So the different stages of a star, as I say, correspond to different places in this chart. So the main sequence star, which is a relatively young star, in which you have only helium burning in the center of the star are placed in this main sequence star, depending on the initial mass of the star. We're talking about the stars in the towards the red part of the spectrum, or for heavier stars more to the left. Then you have red giants in which the helium being accumulated as a product of the hydrogen burning is becoming bigger and bigger, and you have helium burning in a small surface around this helium sphere. And this is the so-called red giant region of the star. Then you have horizontal branch starting with the helium. This is the helium flash, or the helium start to get burned. You have both helium and hydrogen burning. This is horizontal branch for the population, and then finally you get asymptotic giant starting which you have additional burning of heavier elements. So I say all this because the presence of an action production in the nuclear environment of a star may play an important role and may modify some of the observables that are linked with this chart. Why is that? This is because in the same case of neutrinos, even if you have a very weak production probability of these particles, these are so freely interacting that they can escape immediately the star. So the difference between a feebly interacting particle is that as soon as it is produced, it escapes, while a strongly interacting particle cannot escape the star and start moving around, and then they do at the end, when integrated over the huge volume of the star or the nucleus of the star, they represent a non-negligible energy drain from the star, and it may modify the time that the star spends in a particular period of its life. So this is a nice qualitative description of what happens. This is the emission rate of the effective emission rate of these particles outside the star versus the interaction strength of the particles. So if you have a extremely weak, practically zero, of course nothing happens. But if you have a very strong coupling, again, the emission rate, effective emission rate is also small because the particles do not escape. That's why photons, electrons, only a surface emission, only the last part of the star is really emitting energy outside the star. And the maximum effect happens with relatively few interactions, like in the case of neutrinos or force actions in the axis. So let me list a little bit how can this be translated into real observables and what is the people is using to constrain action properties or to identify the presence of an action in the stellar evolution. So, for example, one of the most important aspects is what is called the tip of the red giant branch. So this moment here in which the helium flash starts and then the star moves towards the horizontal branch. The point this happens is very sensitive to additional cooling mechanism. So if you have additional cooling by action emission, that this is also generated to other exotic emission of other particles, it will move the tip of this RGB or red giant branch to higher luminosities. So in addition, this emission of particles reduce the lifetime of the helium burning phase. So it will depopulate the stars present in this region, in the horizontal branch. So one usually defines what is called the R parameter, which is the ratio between the number of particles in the horizontal branch over the number of particles in the red giant branch. And this is sensitive to the presence of action. Another important topic is white dwarfs. White dwarfs are down here, and they represent the latest stage of some stars, the ones with less mass, when the nuclear fuel have been exhausted, and then they have a very simple evolution, basically they have a thermal process, very simple. So they are very well understood. So they are very well modeled, and usually when you have this type of systems, you are sensitive to exotic, to the presence of exotic mechanisms like the possible emission of action. And I will show in a moment. The wide dwarf immunosensitive function is a tool that has been used to constrain action. Yeah.
Can we have astrophysical observations to make us think that this plot might not be exactly correct? Like you're talking about modifying the plot in some way, but are there observations to back that up? Make us think that that might be reasonable?
As I will show now, there are observations that that they are in tension with expectations from standard modeling. Of course, in astrophysics, you can never be sure because they are complex. Sometimes they are complex objects, and you may have standard effects that are not properly accounted in the standard model. So you have to be careful. There are systematic effects, but there are some tension. But in general, it depends. For example, in white dwarfs, it's difficult to understand that attention with expectations is an unaccounted standard effect because they are relatively simple objects. But in other cases, I will mention now, we have this blue loop that we say here, which is also sensitive to the presence of actions of other exotic pooling mechanisms. Okay, this is more risky to claim that attention with expectations corresponds to new physics. So, okay, to use astrophysics in this sense to study new physics is a bit delicate because you can always have standard processes that are not well understood. Also.
Thank you.
Okay, this is the blue loop. The loop is this path that some stars do when they start the helium burning phase. They move quickly to cooler to bluer part of the spectrum, and they go back to the red part of the spectrum, and this is called the blue loop. And the time they spend in this transient is quite sensitive to additional pooling also. So this has been used to constrain the presence of action. Well, this goes a little bit beyond action. So any exotic mechanism that produce additional cooling and acceleration of the evolution of the star in that period would account for this change in these observables. Now I go to the interpretation in terms of action, which is what interests us. And the nice thing is that different type of stars have different nuclear environments in the core, and therefore they probe different mechanisms, different action production mechanisms involving different couplings. In particular, most of the times action photon coupling and some case action electron coupling, and in some particular case also action nuclear coupling. So, for example, this is a very nice plot from some collaborators, Giulianotti and collaborators, in which it illustrates a little bit. Okay, for example, the Primakov production of actions, which is based on the action photon coupling in the nuclear plasma of the star, and is based on the action photon coupling, is relevant in environments with low density, relatively low density, high temperature, while mechanisms involving the action electron coupling, like Compton or action restranum, both involving action electron coupling, are relevant more in the case of Compton low density, high temperature, and in case of restranum high density. So this means that, for example, well, white dwarf stars are in this part of this plot, which shows temperature versus density of the core of the star, and therefore, in this case, action electron coupling processes are more relevant compared to action photon coupling. So if we find an extra cooling in this type of stars, it could be interpreted as action electron coupling rather than action photon coupling. And this is different from the case of horizontal prime stars or in the sun, in which action photon coupling would be more relevant for this purpose, not for it. So this is why I will classify now the different observations in interpretations in terms of bounds on the action photon coupling or the action electron coupling. For example, okay, I will not go too much into detail, only I'm going to present the most relevant results that are going to constrain our parameter, our spatial parameter. So for example, the R parameter observable that I mentioned before in HB stars, horizontal range stars, is currently the most probably the most relevant bound coming from astrophysics on the action photon coupling. This must be taken into account. The latest results points to an upper bound of 0.66 10 to minus 10 divisions G minus 1 coming from analysis of several population of horizontal range stars. So I will not go into detail, but basically, well, this R parameter can be linked with the presence of an action, having an action photon coupling in this way. And as you can see, there is another dependency, which is Y, which is the helium mass fraction, which affects the analysis. So you need to know what is the initial helium mass fraction in the star. And okay, intriguing feature here is that the best fit, even for conservative values of this Y factor, the best fit of the data seems to favor the presence of an action photon coupling, which is different from zero. Okay, if you express this in terms of an interval, you get something like that. And this is sometimes referred in the literature as the HB hint. It's not statistically relevant. This is 2 sigma compatible with absence of coupling. So it's not something that one would take very seriously if it were not because there are other observables also suggesting a similar thing in other channels. We're seeing, yeah.
I'm sorry, I probably missed this, but why would we say that the coupling between the axion and the electron is negligible?
Well, we should not. In fact, a more complete analysis should allow for both, and I have plot that makes the combine. So you let both free, and you get that to the region.
So there's no motivated choice to say that the axion and the electron would have weaker coupling in.
No, only if you are constrained by some reason, you are constrained only to models that do not have action electron coupling. So you want to explain this with models like Kaiser, that they don't have action electron coupling.
Sure.
That would be the only motivation. But you're right. In general, this is not. This is therefore not a super strong bound on the action.
Could you just clarify why the expectation from the standard model of evolution stars it's different from the like why you need the accent and you can explain this with standard model evolution systems?
Well, you don't need. It's only that if you have an action above this value, then you will have a tension. You would see a strong difference that you don't. So this allows you to constrain that. It's not that you need. Well, you need it only to a small, very small extent if you believe this hit, but it's not statistically relevant. There is another.
Hi. I always hear that okay, so recently there was this contentious xenon 1 time access, and then they had like little bounds on, some bounds on GAE and GA gamma, but the bounds are on the product of GAE and GA gamma. And I always hear that your intention is the stellar constraint, so I'm trying to understand what's going on. But on this slide, it says that the assuming GAE is negligible, can we constrain GAE using this horizontal branch?
Yes, I will show you in a moment. But there are better constraints on this GAE from the RGB stars alone and from the white ones.
Oh, okay. So actually the GAE and GA gamma, they're constrained by different kinds of stars.
Yes.
Oh.
I think the only stellar system that that could be explained by both, and therefore it's the generated this one, if I'm not mistaken.
Oh, okay,
But all the other hints or bounds that we have from astrophysics, they either constrain action electron or action photon.
right, okay.
For white dwarfs, we constrain only action electron because action photon coupling is not relevant in white dwarfs.
So for some weird reason, if you, okay, so G, E and G again, they're constrained by, okay, by two different kinds of stars, branches. And when you multiply those two bounds together, is it possible to like somehow have a weaker bound? That is not in, so there is not intention with the
Yes.
the one-time exist.
To some extent, you can do it,
Oh.
but okay, you put all together, and I have a plot later on
Okay,
showing if you put everything together, strictly combined,
yeah,
you get a combined limit on action electron, action photon,
yeah,
and you have this effect. You can choose to relax one of them with respect to the other. But at the end, you cannot do this arbitrarily.
yeah.
And I think at the end you have very little room, if any, with
Okay,
the synonym set.
okay, cool. Yeah, thank you.
So this is a summary. Okay, I will explain very briefly the most important argument, but there are other arguments. So you can use the sun itself. This is interesting because sometimes you can decide not to trust too much one of these limits because they involve stellar physics, which are more complex. But maybe it's good to know that there is more solid physics, like solar physics, that is pretty well known, that can be used also to constrain. For example, okay, this is a semi-quantitative plot. You should understand this as a bounds on the action gamma action photon coupling. We divide the 10 into a 10, and this is arguments coming from the sun, purely neutrinos from the sun. It bounds the only using this information. It bounds the action photon coupling to 7, 10 to 10. You have the global analysis using also heliosismology, all the solar information bounds already this before. And the most stringent bound is the one I just mentioned, the HV star, the air parameter. So we have a level 0.65, 0.66, with some hint. So the meaning of this analysis is away from 0. There are other arguments also using HV stars. The blue loop that I mentioned before, it also gives a constraint on the action photon coupling, which is less strong, probably more uncertain. But okay, this is probably the overall picture on the taking only the action photon coupling, but with this caveat that I mentioned before, that some of these stars, the HV stars, could also be explained with some action electron coupling. Therefore, the right thing is to do a combination of both things. If I go to my standard plot with the yellow band and the experiment, then I see that the bound of the horizontal branch stars are somewhere here. So it's quite strong bound at the same level of the helioscopes or helioscopes experiments that I will describe tomorrow or after tomorrow. Provide an upper bound of the action photon coupling, which is at the same level of the best astrophysical limit on this bound. And this hint is right below it. So this is probably the 1 sigma region that could seems to hint of that. That's interesting because it's right below experimental sensitivity, so it will be explored pretty soon by different experiments that I only mentioned.
And where does
the xenon 110 bound fit on this plot?
Xenon 1 cannot be plotted in here because it involves the action electron coupling. So it involves, depending on interpretation, it involves the action electron coupling or a product of action electron and action photon. So you cannot put it in a clean way in a plot that only shows action photon.
Okay,
I will show now the action electron plot, and then you can see it. I don't have it completely updated with the latest xenon that I have there. Overall underground experiment xenon lux. So let's move to white dwarf. White dwarf, as I mentioned, they are very well modeled stars, very simple stars, and any change in the evolution could be a hint of a exotic cooling mechanism, and interpreted as an action. It would point to an action coupled to electrons because of the environment, nuclear environment of the star. And indeed, the most powerful observable in this respect is the so-called white dwarf luminosity function, which is this plot that you see here, which is nothing else that take a big population of white dwarfs and plot them in beams of luminosity. So basically, this is closely related to the evolution of this white dwarf. When they evolve, they change luminosity, and therefore the number of white dwarf in every beam of luminosity will reflect how are they evolving throughout their lifetime. So this can be reproduced by models, accurately. Okay, there is an overall good agreement that can be used to constrain the presence of exotic processes that could speed up at some point this evolution. And in particular, this middle part of the luminosity is the one that is more sensitive. And what you see here, these different lines are different models of the evolution of the white dwarfs, in which you have added artificially additional cooling mechanism. And you can see that this depletes this depletes the presence of stars in these beams here if you add this extra cooling, and it's pretty sensitive if when interpreted in terms of action photocoupling. For example, okay, this is a bit difficult to interpret because these authors of this plot, they use the mass of the action, but this is not really accurate. I mean, they use a particular model in which mass and action electron coupling is univocally linked, and this is not the generic case. So it's better to express this in terms of action electron coupling. It's more correct. And okay, so these experimental points, and you can see that for these values you have a strong tension, and this can be translated into a bound on the action electron coupling, which is of the order of a few times to the minus 13. Yes.
What is it about the physics going on inside of white dwarfs that makes them specifically sensitive to the axion electron coupling?
Well, basically is that what you have is this process Compton production of actions and Bremsstrahlung action Bremsstrahlung. So basically, these two diagrams that I showed before. Okay, these two effects in the plasma of the star. You have these things happening. They are favored over other process involving action photon, mostly due to the high density. So the white dwarf high density stars. So these two processes are favored.
And so I guess since they're high density, it would be mostly Bremsstrahlung that's happening.
It's mostly, well, depends on the type of white dwarf, but you can see, okay, it's difficult to see, but you have this number that you see here is the relative emission rate for every one of these three processes, depending on the where you're in this plot. So you can see that Bremsstrahlung, okay, Bremsstrahlung for white dwarf up here are quite important. One, Compton is also quite important compared to Primakov that is negligible for this. You see 10 to the minus 12 and minus 8.
Looks like
Yeah.
Primakov for 10 to the minus 4 might be highly relevant. Is that true?
Yeah, for these ones, but you still have you are close to much higher Compton probability. So still the electron coupling weights over.
Okay.
Action for
And what are the values on that plot? The like say Primakov 10 to the minus 4. What is that 10 to the minus 4?
This is emission rate.
Emission rate.
Emission rate in relative terms. So it's not.
Okay, thank you.
Welcome.
On this spot, a question I always had, like, why Axon? You can explain this excess for another example, like beyond this model.
It could be exotic neutrinos, couplings. It could be hidden photons. It could be some other. It's not necessarily Axon. What is nice that there is a nice paper that they quote, not this one, but another, the paper that combines that once you combine all these slight hints, if there is indeed a preference for an Axon interpretation versus other exotic interpretations. But if you take a single of these hints, it may not be necessarily an Axon. It could be some exotic cooling process at the start. This could be produced by other type of phenomena, exotic phenomena, other freely interacting particles being emitted. And there are some studies of exotic neutrino couplings or hidden photon emission or some other. So, so this is okay. I put here the hint that you can see also the order of magnitude. This can be interpreted as a bound on the axial electron coupling, and can also interpret as a mild hint because the actual dots are a little bit in tension with the continuous line that is the no fully standard model, no additional cooling. So this is called the white dwarf luminosity function bound or hint also in this respect, and is the most important bound on the axial electron coupling, together with the RGB star, which also bound the axial electron at similar level. There's another observation which is a bit funny. It's completely independent from the previous one. So this is another way of measuring the cooling of a white dwarf using observation of single white dwarfs, the ones that show a period, because some of these objects are oscillating somehow. They show oscillation in the luminosity, and this period may evolve. It actually evolves in the long term, because it depends on the cooling of the overall star. And this is something that is known. It's difficult to observe, but it can be observed if you have observations separated many years apart of the same object. And the evolution of the period of the period of luminosity is a directly test of the cooling rate of this. So you can actually measure this, and this has been done with a number of stars, not many. I have a table here from this paper with 5 stars. By the way, these are papers that are not related with axons. So this is physics papers, and all of them tend to show a cooling rate which is slightly larger than expected. And of course, this is a bit complex to extract conclusion from here, but when interpreted in terms of action, it gives values that are very similar to the one obtained from the white dwarf luminosity function. It's a bit intriguing. Still, when you combine everything together statistically, we are talking about maximum 2, in some cases 3 sigma effects. So it's not really compelling for astrophysical observation, but it's intriguing. And then you have the RGB tip. This is what I mentioned before, that the luminosity of the tip of the red giant branch is sensitive to the presence of additional cooling. And again, this is mostly driven by, it would be mostly driven by an axion electron coupling. And this can be translated into a bound on the axion electron coupling. And in fact, there is a very, very recent analysis from this very year with much more statistics that can improve. And you see they get a bound on the axion electron coupling, which is of the same level of the white dwarf. And then there is the possibility of combining all this together. But this result is not completely updated with this latest bound from this year. And And as I said, when one combines everything together, the hint becomes something at the level of 3 sigma, which is starting to be interesting, but probably does not constitute a claim at all. Similar plot as before, using the action electron coupling, we have information from the Waldorf luminosity function, from the Waldorf variables, this variability in the period of single stars, and the RGBT, which is producing now the strongest bound on the action electron coupling. And again, these are 1 point something or 2, 3, 10 to minus 13. This is the order of magnitude we are talking about when talking about action electron coupling. And this is the equivalent plot that in the action electron coupling that is the first time I show it, because it's much less interesting than the action photon coupling. The plot is practically dominated by astrophysics. So you have the equivalent of the action of the yellow band in the action electron coupling would be something like that. And basically, astrophysics sets a limit at the order of 10 to minus 13, a bit more. And if you believe this hint, you will have this band here that would be fitting best astrophysics data. And this is what you asked before. So this is underground experiments. So roughly, all of them are very similar, xenon, lux, and so these experiments look for winds. They can also be interpreted in terms of actions. So actions coming from the sun. This is how this limit is set. Purely on the action electron coupling. There is also the interpretation combined action electron action photon that is not represented in this plot. This is only action electron coupling. Yes.
Just to make sure I understand what's going on in this plot. So this is showing excluded regions except for the white dwarf hint, and that would be a preferred region, but all the other colored regions are excluded.
Yeah. I always use the same color code. So blue regions for me are bounds, excluded regions based on astrophysics or observations of the solar actions, helioscopes or similar observation. And green regions are cosmologically dependent regions. So arguments coming from cosmology or experiments looking for action dark matter. And the yellow band is the yellow band. So theory models.
I'm guessing the ultralight actions like the mass in the range 10 to the minus 20 eV and all of that are not at all constrained by astrophysics, right? Only by cosmology. Because
No.
I mean, I also see the lower bound in this process like 10 to the minus 7 EV or something like that.
No, this is continuous arbitrarily. So there is no lower bound on this process. So they are constraints. They are constrained.
Astrophysics can also constrain these very, very small masses. Okay.
In fact, it's the opposite. It's heavier. These bounds, if you go to heavier masses, they start getting weaker.
I see.
Because if you have an action that is relatively heavy, then they may not be produced in the star. But if it's light, then it's absolutely no.
Because they're independent on the mass.
It's independent of it. This can be seen better. So maybe I go back to this. No, this cannot be seen here. Okay. Look, this is a bigger range version of the same plot always, and you can see horizontal branch stars. It's flat, but at some point it goes up, and the solar version of the same limit that I mentioned briefly. So this is basically using solar physics and what we know about sun, what would change in the life of the sun or in the neutrino emission on heliosismology due to an action production. Again, it is flat with mass up to some value which it goes up.
What is plane radius in that?
What is that?
Plane radius.
The gamma rays.
No,
Oh.
GM radius. Bottom left.
DM radius. Okay, these are projections of some kind of experiment. So I will describe that work. These are experimental limits, and the faded regions are projections of experimental limits. So experiments that do not exist yet, but they have been proposed. I will talk about this tomorrow. Okay. White dwarfs. Okay, this is the summary of action electron coupling. This is a global fit that we were mentioning before. So you could take all together and assume you don't make any assumptions. You assume you may have both action photon action electron at play in all these hints, and then you can have combined exclusions. Of course, if you assume one of these is small, you get the other one relaxed. You can see more information in this paper. I think the overall situation is that you have a quite strong coupling, quite strong bound from astrophysics on both action electron and action photon couplings. At the same time, there is a hint that is relevant at the 2 to 3 sigma level, so it's not super strong, not to be taken too seriously, but it's interesting the fact that this region will be, it's relatively close to experiments and will be explored in the next years by several experiments. So this is the important message to get from here. One more astrophysical observation is the one coming from supernovas, and in particular from the only supernova that has been observed in our galaxy in the neutrino channel, which is this famous supernova 1997.
Yeah, so there are hints on like closing the contours in GAE and GA gamma from all the stars, right? But the results are fairly old, kind of like 2014, whatever. So when will we see like new results on this? And what kind of, as in what extra data do they have to take to constrain this, or like say we found the extra
Data from astrophysics.
yeah.
Well, this result that they mentioned is not so old. It's from 17, and I know these authors are right now preparing a new updated plot from this, and it may be that this is the new plot because I had some help from this person, but it's not yet published. It will be published soon. So this contains, of course, some of the data is old, as you say. The white dwarf variability is old, but then the white dwarf luminosity function, there is new data. Should be already data, but it's not been analyzed from this purpose, from Gaia, for example. I think. This bound from RGB tip is quite recent. So you see it's a few months, and it's relatively new data from new surveys and new statistical better estimation of systematics, things like that. So it's a combination. In fact, this result is what is brought in this new combination analysis that is in preparation. So there is some activity here. So it's not all data and everything is static. So this new analysis ongoing and new data will come. So.
Right. So the main thing is that people need time to like look at the sun and then collect data and then like we just need to like collect more data. Is that the main? Well,
the data from that I'm talking now is data from astrophysical, from astronomical catalog. So this is big observation missions like Gaia, things like that. And what you need is a team of people that really digs into the data and extract the observables that are of interest for actions, because this is not a mainstream activity on astronomy. So basically, yeah. But I don't think this picture will change too much. It may give some. The hint may evolve. It may wash out this hint or make it more important. But I don't think it will move the bound too much.
Oh, okay. Yeah, I'm just like slightly impatient. Okay, thank you.
Yeah, we are.
Because it's kind of annoying, right? It's like almost there, but not quite there. I'm like, okay.
Yeah, I think okay. Personally, my field of activity is action oscilloscope. So I'm particularly interested in this because action oscilloscope will be sensitive. Jackson in particular, I will talk about this tomorrow after tomorrow. Will be sensitive to this range of updates in direct detection. So I will actually measure the actions. So this will be settled probably by action oscilloscopes earlier than by astrophysics, probably. So I'm also impatient, but for testing my own experience. So actions can also have effects in supernova explosions, and this is completely different nuclear environment, and now super high densities and different nuclear matter. So here the process that is leading a possible effect is the action nuclear coupling, and this gives a very strong coupling, the very strong bound. And the argument is the following: you probably know that this supernova that exploded in the 87. It was detected by several neutrino detectors. So we have a few neutrino detectors that are linked with the explosion. So it was the first and the only supernova neutrinos that have been detected so far. There's the plots from different experiments, Kamikande, IMB, and Batsan. And the duration of, the spread of these events in time can be compared with expectations of supernova explosion models, and they roughly fit expectations. So this was good. We give information on our understanding how the supernova explode, and they can be used to constrain properties of exotic physics that could change this duration of the explosion. And actions are a case. This has been used also for things like exotic neutrino interaction. And okay, there is a lot of literature on this because early papers gave a super strong bound on the action nuclear coupling that then model dependently can be translated into an action bound. You probably have seen in several papers that there is a very strong upper bound on the action photon on the action mass coming from this argument, which is depending on the paper even as low as the electron volt. Well, this has been revised quite a lot in recent years because the field start being more delicate in what is excluded or not from this argument, because there are experiments with sensitivity to this area. So this has been relaxed considerably. And at the moment, okay, this is a very recent result in which translates the observation of these neutrino events from the supernova on a combined bound of action proton and action neutron coupling. So depending on the models, both action proton, action neutron couplings could produce an effect, and in a combined way you have this sort of bound. And this can be roughly translated into a bound of the action mass. But of course, as I mentioned before, going from coupling to mass involves model-specific things. So this is model dependent. But in a conservative way, you could say something at the level of 20 electron volts. This is quoted, for example, in the Partido de Tabuk as an upper limit on the action mass, but it has to be taken with with some caution, because there is a lot of uncertainties, the sparse neutrino data. All this is based on these few neutrinos that were detected. Also, the modeling of supernova, there may be still big systematic uncertainties. Some models even do not predict explosion at all, things like that. So, anyway, there is a lot of literature about this topic right now. And I leave you in the next slide with a summary of the bounds coming from astrophysics, coming from this review that I have mentioned several times in the previous classes. And then let me mention that stars can be axion factories, so in the sense that they offer opportunity for detection. I will come back to this in the experiment session, because this opens a way of detecting action using action helioscope, basically actions from the sun, which is the closest star. And therefore, they were more promising for this. I will come back to this. And before finishing, I want to mention something else that it has been discussed a lot in recent years. There have been many papers on this as a possible hint for action. In this case, action on light particles. You already have heard about this. This is the high energy photon propagation over large distances. So basically, it's the same action photon mixing mechanism that I mentioned already yesterday, and I will come back to this in the experiment part, because it's the basis of many experiments. But happening in the intergalactic medium, intergalactic magnetic fields of the universe. This means that photons may go through very large scale magnetic fields in the universe, and then they may mix with action. And at the end, this mixing, what it does is to reduce the effective opacity of the universe to these photons. So probably at very high energies, the universe is opaque to photons, because they must interact with extragalactic background light, this very deep diffuse light from a star that is there in the intergalactic medium. But there are so large distances involved that at the end you have this effect is relevant, this pre-production, and you should not observe photons of given energy, very high energy. And it was some claims some years ago that the observations from experiments like gamma ray telescopes were not compatible with the model. So they were seeing either photons of too high energy, and that should coming from very distant sources, so they should not arrive the Earth, or spectra which were harder than expected, so with more component in the high energy that expected compared to the expectations from the emission spectra combined with the propagation in the universe. So it was claimed that this could be the effect of an action mixing, photon to action mixing in these fields. And there were many models using magnetic fields at the source, using magnetic fields in the galactic medium, or even using fields in the Milky Way. So roughly, the overall story pointed that in order to match observations with models, you need parameters for this action to photon mixing in the ballpark of very low couplings and very low masses and relatively high coupling. So this is all these regions that you have been seeing in make plots in this area correspond to this type of results. And you can see they are far from the yellow band, so this cannot be reduced in action. This would be enough if this is true. At the moment, the issue is quite controversial, and the consensus is that it's not clear if there is anything here. There are some papers producing transparency hints that they are called. I call them here in yellow. Some of them, there are more. And there are also papers that use this effect and the absence of this effect in some data to constrain. And then there are these blue regions here. So they overlap quite a lot. If you take this at face value, you would say that there are still regions that are allowed for this hint. But in overall, the situation is a bit, one should be quite skeptical. In any case, this is again region that will be explored soon by experiments like Aug17 and Jackson. I will talk about this tomorrow. There are a lot of papers and some controversy here. So I think I'm done for today, just on time. So yeah, so I finish with astrophysics, and tomorrow I will start with action detection. Do you have any questions or what?
Any questions? Any more questions? If not, thanks, Igor, for the lecture.